So let's thank Elisa again. So the next talk is given by Ramakers, and it's on PaperPulse.
Okay, so I'm Ramakers, I'm at Delft University, and this talk will be about PaperPulse, a design tool that allows you to make paper interactive. So our work is motivated by the observation that recently there has been increasing interest in making paper interactive by augmenting it with electronics. Like we've seen interactive paper sheets and books and even paper devices like headphones by just putting electronics on it and attaching components on it. And when we look on the technology side, we see that there's a wide variety of technologies available to make electronic circuits on paper, like conductive inkjet printing, which you can use to very precisely print conductive circuits on paper. We have milling machines to cut traces out of conductive sheets, and we have conductive pens to draw traces manually on paper. But when we look at the people who regularly work with paper, like designers who create posters and invitation cards, for example, they often don't have like a background in electronics and programming to make paper interactive. So that's the goal of PaperPulse. It allows designers without electronics and programming knowledge to make paper interactive, more specifically to make standalone paper artifacts by augmenting it with electronics. So this is such an artifact you can create with our tool. It's like a small game, and when you turn it on, a sequence of LEDs start to loop. And you have to press a button at the right moment when the LED above it lights up, and then the buzzer goes off. So this is only one example of stuff you can make with our design tool. And here I briefly show on a high level how this is done with our tool. So you first of all add all the images, and you overlay it with components. And then we have like a logic recorder to specify logic, on which I will explain in more detail later. And once you specified all the logic, you can actually test it already out in a simulator. So when you're satisfied with your design, you just press the print button, and then we generate all the electronic circuits, and we generate also the code for the microcontroller. Then we can print out these electronic circuits with a printer that has some conductive ink in it. And then we provide instructions for the user on how to assemble this. So he has to attach components and cut out and fold paper in different ways. Afterwards, he just puts everything together. He uploads the code that we generated on the microcontroller, and you can basically power the thing with a small battery. And then you have like a standalone paper artifact. So our work is highly related to the Midas design tool, which focused on creating capacitive touchpads for mainly to enrich existing devices with additional buttons. Our work is different, so PaperPulse is different in that it allows you to create standalone paper artifacts, and especially for those who don't have any programming and electronics knowledge. So these are the three fundamental principles on which PaperPulse is built. So it provides you to make standalone paper artifacts because we integrate input-output components as well as a microcontroller in the paper design. So we contribute 3 widget families to do so. We have off-the-shelf widgets, paper membrane widgets, and pull chain widgets. So each of these widget families are different, but they still provide all basic controls like switches, buttons, and sliders. So the first category, the off-the-shelf widgets, are basically existing components that we attach to flexible substrates so that you can more easily attach it to paper. So there's some sticky and conductive side on the back, so you can just place it on paper and then it connects to the circuit. And this is of course inspired by work that was presented last year at KAI. So off-the-shelf widgets are very easy to connect. You just put them on paper and it works. But the paper membrane widgets that we have require a bit more assembly work since they're entirely constructed out of paper. But the benefit that you get from them is that you can just put your own design on top of it, and you can scale it to any size. The way this is built is that you have like a bottom layer, there's a space on top, and then you have a top layer. So when you press the top layer, it make contact with the bottom layer and you have a closed circuit. So similar to the paper membrane widgets, we have pull chain widgets, which also are entirely designed out of paper, but are based on the interaction principle of using pulling and pushing interaction techniques. So this is how this looks like when you fabricate one. And we constructed them by interweaving paper layers inside each other. Actually, you can combine all these different widget families in a single design. Like you see here in our paper game, we have a pull chain switch, an off-the-shelf LED, and a paper membrane push button. So we can integrate that in a single design because we created a unified 3-layering approach. So every design created with PaperPulse always consists out of 3 layers. And every widget that you add to the design contributes to some of these 3 layers. So besides the input and output components that are available, we also integrate a microcontroller inside the paper design. So here you see the thread needle, which is a commercially available microcontroller that has flat pins, so you can easily attach it to paper with conductive tape. But actually, you can use any other kind of microcontroller that runs the micro framework. So also the Arduino, which is of course harder to attach to paper because it doesn't have any flat pins. So we attached it to the paper with bulldog clips. The second fundamental principle on which PaperPulse is built is that it doesn't require any programming knowledge, electronic knowledge, because we generate all the circuits. So therefore we adapted a traditional A-star algorithm to efficiently use pins on the microcontroller. And we also at the same time we try to minimize the number of intersecting circuits, intersecting circuit traces, because at these places the user has to place a bridge. So this is use the same principle with this sticker metaphor as the off-the-shelf widgets do. So the last fundamental principle of PaperPulse is that it doesn't require any programming knowledge. And that's because we came up with a logic specification technique called Pulsation that is fairly easy but still flexible enough. So in the past there have been other approaches that allows the user to specify software without actually writing code, and most of these are based on the idea that you have building blocks that you can arrange. And but the thing with this approach is that often still require you to have some exposure to programming languages, since they use the same constructs like loops and variables. In contrast, Pulsation is actually built around the idea of that you only have 2 kinds of functional relationships, if-then and map-to rules. So this is how such an if-then rule is specified. For example, with our paper game, when the switch is on, all LEDs start to blink. And so that's specified by turning one LED on and back off, and we do that for all the LEDs, and we specify some offsets, timing offsets, so that they blink one at a time. So the question now is, how does the user specify these rules? And that's done using a program by demonstration approach. So the idea is that the user just demonstrates the input and output that needs to happen, and that the system records this and afterwards translates that in code for the microcontroller. So the user just demonstrates that the switch goes on, and he demonstrates that the switch, that all the LEDs go to 100 and back to 0. So this idea of program by demonstration has been used in the past by systems like Example and Pickle. But the main challenge that we experienced with program by demonstration was that it's often hard to specify timing relations between input actions. For example, how do you specify that input can happen in any order? For example, you can press these 3 buttons in any order for something to happen. And using strictly a program by demonstration approach, you would have to demonstrate all these kinds of combinations. So you have to enter ABC, CBA, and BCA, for example. So in contrast to, so this of course takes some time, and so to solve that we augment the demonstrated samples with dialog boxes for fine-tuning these timing properties. So you can add some offsets to actions, and you can specify, for example, that input needs to happen simultaneously in a random order or sequentially. This is another example that uses if-then rules. It's actually like a special birthday or invitation card to a birthday, where you need to know the year of birth of the person before the date of the birthday party is revealed. This is an example that uses multiple if-then rules, where yeah, it's actually a restaurant, an interactive restaurant menu where you can use a slider to filter through the menu options, and you just input the maximum price. So in contrast to if-then rules, we also have map-to rules that continuously map a derived parameter of the input set to the output set. For example, if you want to map the value of a slider to the brightness of the LED, or even like a sub-range of the brightness of the LED, or we can even invert the signal if we want. So in this example, the value of the slider, if we increase the value of the slider, one LED will fade in and the other one will fade out. But this is just one example of a mapping rule that we can use. We actually have much more derived parameters. For example, in this example, the value of the slider is mapped to the number of LEDs that light up. Or in this prototype, the number of times you press a button is mapped to the number of LEDs that light up. This is actually a diet card, which you can track your food consumption during the day. And after the day, you can just reset the card. This example makes use of speed, so it maps the speed at which you tap two buttons to the number of LEDs that light up. And then the final example, we use a microphone to register the intensity of the music and map that to the pattern of to the number of LEDs that light up. So the question now is, does this all work, and are designers able to design and make paper interactive with PaperPulse? So we recruited 4 designers. They got who have like no or limited experience with program and electronics, and they had an introduction to the system, and afterwards they were able to make something themselves. And actually they came up with quite some cool prototypes, like an electronic rock paper scissors game, or like a paper system to exercise math skills, like basic sums. But details on the study can be found in the paper. So to conclude, PaperPulse allows you to create standalone paper artifacts because we integrate input-output components as well as a microcontroller. No electronic knowledge is needed because we generate the circuit, and the circuit can be printed out with a printer filled with conductive ink. And we don't require any programming knowledge because we have a simple but flexible way of how to specify logic, which we call pulsation. So actually the vision of this whole project is that making paper interactive will become as easy as as designing for regular papers like you do in Photoshop and Illustrator. And because of that, any paper could become interactive, from the examples that we've shown here in the presentations to, for example, packaging material or even business cards. So this concludes the talk, and we also have a demo here. So if you haven't checked that out, we brought lots of prototypes with us, and you can still come by for one day, I guess. Thanks.
So we have 5 minutes for questions, so if you just come up to the microphone.
Hi, great presentation. Jennifer Jacobs from the Media Lab. I'm really excited about the fact that you developed a CAD environment that combines the design for the paper with the creation of the electronics. One of the really amazing things about paper is that it can also be readily shaped by the human hand, so you can fold it and draw on it. And I'm wondering if you've thought about ways in the future for design decisions that people make when manually working with paper can be used to inform the design that's then in the software and through that iterative process.
So we support some of these origami and pop-up techniques that are used in art and in pop-up books. So we have like these pull chain sliders that you can assemble. But yeah, indeed, you can also manually draw circuits on the sheet. But I think with more complex, when the circuit becomes more complex, it's I think quite hard to do that manually because you have to really think of how you lay out the traces. Even if you would know about electronics, then it's still quite hard to precisely lay it out so that you don't have like lots of bridges and lots of overlaps. So. I think that's one of the benefits of having such a tool. But indeed, we want to look into the future of how you can also, for example, make 3D shapes with this. So when you make flat design and then you print it out and you fold it to a 3D shape, for example.
Just a quick follow-up. Do you have thoughts about if it would be potentially beneficial for someone to start by drawing circuits on the paper and then move into a software environment where they can have a greater level of control, or the system aid them in the process of laying out a more complex circuit? Or do you think that it's purely a one-way process from the software to the physical space?
Yeah, it could indeed be a good idea, because now we have now the design process, if you want to do multiple iterations, you have to do that in the software, so you never really have the feel of the paper. So that might be a good idea to also include that, so that you first start with drawing the circuit and then transition to the software to make a more high fidelity prototype, and print that out. So
thank you.
So maybe I also ask a question. I think it's really a great tool because it abstracts away all the details, but have you also thought about kind of maybe showing more and more details to people who are kind of want to learn electronics? Any thoughts on that?
Yeah, we at the moment we actually don't do that, but that might be a good idea also to learn people things, because with our tool at the moment they don't learn more about electronics and programming, but could be a good solution, because with the rules that we have, they have some flexibility to specify like relations between components, but if you really want to go further, probably you still have to transition to real programming code. So I think having this basic solution in the beginning allows you to introduce people to programming while still being able to already make something practical, and you can probably also do that for electronics then.
Okay, so let's thank Raf for the great talk again.